We've been talking about functions and limits. I'd like to point out that even though I gave you some graphical examples to illustrate some of the concepts, the graphical nature of the functions hasn't come into play. Compute these things. In a sense, we haven't talked about continuity. That's something that we will do. Let's talk about some of the properties that limits have. Just as when you were working with sequences, you could break them down, multiply them, divide them, and what have you. There's a number of things you can do with functions and limits. Theorem on the operations on limits. As always, we let A be a subset of R, F, and potentially G. B functions from A to R, C, limit point of A, alpha some constant, R. We'll further assume that the limit of x goes to C of the function f is L, and that the limit of x goes to C of function G is M. Then the following statements hold. The limit when x goes to C of the absolute value of f at x is the absolute value L. The way to write this is that the limit of the absolute value function of f when x goes to C. These two things. Second statement, which is true. The limit of the sums, the limit of a sum of functions, I should say, is the sum of the limits will be equal to L. The limit of product is the product of the limits. The limit of a scalar multiple of f is the same as the scalar multiple of the limit. And finally, assuming that px is not equal to 0 for every x in A, and that m is not equal to 0, then the limit of the quotient will be equal to the quotient of the limits, L over M. Well, if we had to use the definition of the function to prove these, it would take a fair amount of time for us to do so, but thankfully we do have two theorems, Theorem 14, the operations for sequences and limits, and Theorem 26 that tells us what the link between the limit of a sequence and the limit of a function is, and the proof can be written very quickly, in a few lines. So throughout, we'll have xn as a sequence of values in A, xn never equal to C, xn converges to C, together with f at xn converging to L and p at xn converging to M. The top line is an assumption that we make. The second line is not an assumption that we make, it's a consequence of the first line together with an assumption in the theorem that says that the limit of f at x when x goes to C is L, and the limit g at x when x goes to C is M. So we combine this with the operations to get the following. The limit when x goes to C of the absolute value of f at x would be the limit when n goes to infinity of the absolute value of f at xn, which would be property. The limit, the absolute value, the limit is L. The second statement, the limit when x goes to C of the sum, that would be according to Theorem 26. Same goes here. This is same thing. The limit when n goes to infinity of f at xn plus g at xn, because the sequence xn was arbitrary. And this according to Theorem 14. Right here. Theorem on the operations for limits. The limit when n goes to infinity of f at xn plus the limit when n goes to infinity g at xn, which by assumption L plus n. Do I need to do the other ones? I will not be doing the other ones. Make sure that you would know how to use Theorem 26 and 14 to prove the remaining three statements. And now we come to the equivalent of the Squeeze Theorem, but for function. Let A be a subset of R. Let C be a limit point of A. F and G and H. Three functions from A to R. If the following inequality holds for every x and a, assuming here is not equal to c, and if the limit when x goes to c of f at x is equal to the limit when x goes to c of h at x is equal to L, then the limit when x goes to c at x is also equal to L. When we say this statement here, we are saying that the limit exists, and that both limits are the same, right? So there's a double statement. At any rate, the conclusion that the limit of the middle function also exists and has to take on the same value, L. How do we prove that? We're going to use theorem 26. Let x and b some sequence in A. Assume, as always, that xn is not equal to c for every n, and that xn converges to c. And this is an arbitrary sequence. We're not picking any specific sequence. According to theorem 26, the limit of f at xn when n goes to infinity will be the same as the limit h at xn when n goes to infinity is equal to L. Since f at xn is smaller than g at xn, smaller than h at xn for every xn not equal to c in A, and we know when goes to infinity f at xn and h at xn both go to L, then by the squeeze theorem, and now I should really specify that it's the squeeze theorem for sequences, the limit when n goes to infinity g at xn is also equal to L. But the original sequence was arbitrary. What we've shown here is that no matter what sequence xn you pick, if it converges to n and all the other assumptions are met, the limit when n goes to infinity of g at xn goes to L as well, which means the limit when x goes to c g at x is equal to L. And that ends the proof. The name of the theorem highlights the fact that this is the function analog of the squeeze theorem for sequences.